Okay. Okay, so the paper was published in 2016 in HPCA, which is high performance. No, HP stands for what? High performance computing, something like that. But anyway, this is the one of the lead conferences in the area of computer architecture. Others are like SCA and DAC. So the paper, it addresses the cache side channel attacks, which one of which we have covered in our previous week. So the attack which we have covered in the previous week was flush plus reload. So this defense actually protects the victim processes against that kind of attacks. Okay, so what is the problem statement? So let's say assume that you have there is a client process which is, let's say, a victim. It is any application or a process which you need to run, and the person or the process or the application which you want to execute, definitely it has code and it also has the data on which the code performs its computation. But let's say that the person who is like, let's say, want to run the application doesn't have enough resources, compute resources, and what does it do is that it submits, it uses the cloud computing or a cloud server to run its application. So what it does is that it submits its code and data to the cloud server. And then the server, what does it do? It runs the submitted application in a virtual machine, which is running on the cloud server. So within the virtual machine, you have that submitted application doing whatever computation it need to do on the data, right? But the thing is, like, you are not the only client. There are other clients at the same time which are also using taking the services from the same server. So let's say there you have another client, which is like a malicious person, adversary with a malicious intent. It has its own code and data, and it also submits its application or request to the cloud server. So then what the cloud server will do is that it will run another virtual machine within which it will be running the application of this second client. And we don't know, like, in advance, we don't have knowledge of like whether who is a victim or who is an attacker. Maybe there is no attacker.Maybe there are like multiple attackers, right? We cannot know it in advance, right? So another virtual machine is launched to run the code application of the second client. But the thing is, like, yes, the two applications are running on two different virtual machines, but both are running on the same physical platform or the cloud server. As a result, what happens that they share the resources. One example of that shared resources is last level cache, for example. And if they are using the last level cache, then you can launch the side channel attacks, for example, flush plus reload, or another attack which they have mentioned in the paper is prime plus probe, which also actually exploits the shared LLC. Okay, so if that is the case, then the question is like, how can we protect our client or victim from the attack launched by an adversary? So to talk about that, let's first have a look at first some basic discussion about the caches. So again, let's say you have a two-core platform where L1 and L2 are private to the each core, but L3 or LLC is shared. So what happened is, like, just to give you some nomenclature about the caches, if you don't know, caches, they are divided into multiple sets. For example, in this very simple example, we have only two sets, set 0 and set 1. And then within each set, you have, so rows are known as set, and then these vertical columns, they are known as base. So basically here we have two sets, and then each set has 8 ways. So this kind of cache is known as, it is set associative, but eight-way set associative. So which basically means that within each set, you have 8 different data holders or 8 different places where you can place the data. So, and then each cell within a set, it is known as a cache line. And typically cache line is, the size of the cache line is 64 byte. So the granularity of the data which goes in and out of the cache hierarchy is 64 byte. So even like when you want to read a single byte, so you provide the address, but what happens is that memory controller will read the 64 byte aligned size of data and then put it in the cache line. So it basically means that 63 bytes are read like unnecessarily read. They are not needed, but still they will be read anyway. Okay.
That's like used for padding.
Sorry.
The 63 would be padding if it's just reading one actual.
No, it will not be padding. It will read actual, like, let's say the byte which you want to read is located, let's say at address X. So now it depends whether the X is on a boundary of a 64 byte address or not. What does it mean? So let's say this is like address starting from 0 to 63. So here you have 64 bytes, right? So this is byte 0, byte 1, and so on. Now, what is the address of, let's say, this byte? If it is byte 2, the address will be what? If it is 0, 1, 2, address 2, right? So if it is address 2, and then you are providing the address 2, you want to read only this single byte. But this address is not a multiple of 64, right? So what happens is that it will read these all 64 bytes. And while reading it, your required byte will also be read and brought into the cache. Okay. So, but let's say if the address you wanted to read was 0, then it will read all this, starting from this 0, 63 up to 63. But if it is like not at the boundary, then it will read the whole 64 byte chunk which contains your required byte. Okay, so it will not do padding. There is no padding. Whatever data is there actually in the memory, it will be read. Okay. So now when we were talking about the previous slide, we said that LLC is shared between the victim and between the spy and victim, and as a result, it becomes a side channel, right? Which is exploited. And now after reading the previous paper, you know that all the details how it works, right? So how can we defeat this kind of attack? Like specifically, if you keep in mind the previous attack, like flush plus reload, how can we protect against that kind of attack?
Have no differentiation when they do the multiply, if the big is 1.
Yes, but that is like something which is that is correct. What you are saying is correct, but it will work in the case where there is the operation performed depends upon the bit value of the secret key, right? And it is like very specific to the case where you are exploiting the LLC to break the RSA. Let's say you are not using LLC to break the RSA, but some other algorithm where maybe the details of the algorithm are different. So if you like, I want you to think on a more higher level, like your solution, maybe it will work for the case of RSA, but maybe not for some other thing. Yes.
Have disable page turning features like deduplication, where you don't allow.
Yes. So, but then, this was what was also mentioned in the previous paper, but they also mentioned its downside, right?
It's too slow.
Yeah, but let's say I don't want to slow down my virtual machines. I don't want to increase their footprint. So, and that's why I want to keep the deduplication. So what is the root? Think about the root cause. What is the root cause of that, which enables that attack to succeed?
Steal flush command, the routing from everything in memory.
Yeah, that's correct. Okay. When I was teaching the previous course, was some student commented like, the instructor asked the questions and then he wants student to give exactly the same answer which he has in his mind. So it is like, read my mind. Okay, so let's not force you to read my mind. So the root cause is, yeah, that is correct what you said. Yes, if you can like put access control on the CL flush, then you can defeat that. Access control means you can allow only privileged, like for example, the system code to run the CL flush, or only privileged processes to run the CL flush. Then yes, you can. But the main side channel, the side channel was basically coming from shared LLC, right? Let's say if you allow the CL flush, but the LLC is not shared, you will be removing the root cause, right? So here what you can do is like, what was happening is like both the victim and the spy, they were sharing the same LLC, but if we can partition it such that we say, okay, one part of the LLC is reserved only for victim. So the spy cannot access it. Even if there is page sharing, that they are accessing the same page from the physical memory, but when that page is mapped into what it means partitioning, but when it is mapped into the LLC, the same page is mapped here, let's say for the victim, and same page is mapped here for the spy. So if it is partitioned, then spy cannot access the cache locations, same cache locations which are accessed by the victim, and then it will not be able to flush that, even if flush is allowed, right? So what you can do is that you can partition the LLC, but the problem is that, yes, so this is just the proposal, right? So, but this is not was not the new approach or new idea, like partitioning the LLC at the time and when this paper was published. So the similar proposals, they already existed for partitioning the LLC, but only for partitioning the cache, but only for L1, not for LLC, right? So there was no existing architectural support to enable partitioning of the LLC. Yes, it could work for L1, but not for LLC. Okay.
Is that partition dynamically,
Yes, you can, it depends how you design the system, but the solution, they are basing they are developing their solution on the base of CAT, right? Cache allocation technology. So it is dynamic. That particular technology is dynamic. Okay. So you can program like which particular cache sets should be allocated to which particular processes.
so you can increase the partition?
Yes, you can increase the size or reduce the size. Okay. So the second option is that you can do the page coloring to reduce the LLC evictions. So I will explain what is page coloring and how it works, what was the motivation, what was the problem which it solves. But the basic motivation of this approach of page coloring is that you want to reduce the LLC evictions. And when I explain how it works, then you will understand what I'm going to say is that page coloring will still not work for the case where you want to stop the spy from timing its own operation in order to understand, in order to guess what the victim is doing, the operations of the victim. Like for example, in the previous case, it was, are you doing scale or multiply or modulo operation? You can do, but the thing is like there is downside, or there is huge performance cost. Like you can use the page coloring to defeat or to protect against LLC side channels, but there is performance cost. And then also there are limitations that in some settings you can apply it to defeat the attack, but in some other not. Okay, what it means I will explain. So in cases where you want to support the huge pages, there you cannot use the page coloring. I will explain what are huge pages, okay? Hopefully, if there is time. Okay, so the third case is, so that was, so this one, why can't you use partition the LLC? Because at the time the paper was published, there was no architecture support available to enable the partitioning of the LLC. Yes, you can do it for L1, but not for LLC. Page curving, it can defeat the attack, but at a cost of huge performance loss. And also it will work in some cases, but in some other cases it will not. Third option is that what they are proposing is that use the cache allocation technology or CAT. So what is CAT? Basically, like at a very higher level, if you want to understand, what you can do is that you can here, if you look at the figure, you have 8 different ways, W0, W1, and so on. So what you do is that you allocate or you assign different ways to different class of services. Let's say you have class of service 0. So class of service 0 mean that you will, if you have multiple processes running, you will put them into different classes. Like class of service 0, class of service 1, class of service 2, and so on. The basic motivation behind CAT, the problem they wanted to address by providing the support for CAT was this. Like there are some applications which are more critical than others, or which require the higher throughput as compared to the other. So their demand of LLC cache capacity is higher as compared to other applications. So, which basically means that your demand of LLC capacity depends upon your quality of service. Higher the quality of service, required quality of services, higher is the required demand for LLC capacity. So what they said, okay, previously, if they cannot partition the LLC, it means that everyone puts that all the processes put their data in the LLC and then corrupt it, not corrupt it, but pollute it, right? From perspective of one particular process, right? So they said, okay, let's do this. If there is a process which belongs to, let's say, which belongs to class of service 0, so it demands higher quality of service, so we can allocate it higher LLC size, higher LLC capacity. So let's say we can give it out of 8 ways, we can allocate it 4 ways. Okay, so 4 ways are allocated to class of service 0. Now we are left with 4 other ways. Well, what we can do is like, okay, we can define another class of service which has relatively lower quality of service demand and therefore relatively lower LLC capacity demand. So we can say, okay, 3 ways are assigned to the class of service 1. Now we are left with 1 way which we assign to class of service 3, okay, or 2, whatever. Here in this example, for example, we are saying that all the class of service, they have the same quality of service demand and all of them have the same capacity. But the idea is that you can dynamically, you can program particular registers in the processor to specify that which ways, like they belong to which particular class of service, and at most you can have 4 different class of services. And within each class of service, you will have different processes. You can identify that, okay, this particular process belongs to class of service 1 or class of service 2 and so on. Okay. So the motivation behind cache allocation technology or enabling it was to serve various or varying quality of service of different processes. It was not designed to address the security problem. Okay. So, but here in this paper, they are saying that we can repurpose the CAT to achieve higher security, basically to defend against the LLC side channels. Okay. So what they are saying here is like, let's say you have 4 classes, then you can have client 1 and client 2. Both of them are, let's say, they belong to the class of service 2, which means that whenever they read the data from the memory, it will go either to way 2 or way 6. Okay. And let's say there is a client 3, which we don't know, maybe is a spy, let's say, but it belongs to a different class of service. So whenever it reads the data, it's from the memory, its data will go to W3 or W7. Now, let's say if this client one is victim mapped to a different class, client three spy mapped to a different class, it's mean now that client three cannot access, it cannot like, time its own operation to figure out what operations are performed by victim. Why? Because its data is mapped to W3 and W7 here. Let's say W3 and W7, and client data is always mapped to W1 and, sorry, W2 and W6, right? You understand what I mean or not? Any questions?
As those are the three solutions, why specifically, or I should say, out of all the solutions, the paper suggests that the cat is the most optimal. What about the other two solutions? Is there like a certain type of performance that would want to run for those two solutions to be the more optimal, or in what cases would those two other solutions be optimal?
Okay, so you are saying why CAD-based solution is better than the other?
Yeah.
Anyone want one? Why CAD, why their idea is better than the other two?
Or what?
Why their idea, which is like repurposing the CAD to provide the security or to to defend against the LLC side channel is better than partitioning the LLC and page coloring.
So would that just be because of the overhead or the cost it would take to refurbish all these CPUs? It would be much more expensive for. Is that not?
That is true for page coloring. The page coloring will work, but it has high performance cost. That's why it is better. CAD is better as compared to the page coloring. But then why CAD is better than partitioning the LLC?
Is it because you can divide between private data to the core and common data to other cores, so then you can still share information among other cores, which is not private, I guess, to increase performance? And the private keeps private to the core?
Actually, the thing is like, let me try to answer that. The thing is that there was no architectural support, so the cache partitioning will work. Cache partitioning will work, even to defeat the LLC side channel. But for that, you need the hardware support. So it is just an idea. Cache partitioning an idea, right? To realize it, to implement it, you need the hardware support, architectural support inside the processor chip itself, right? At the time they published this paper, there was architectural support available for partitioning, but only for partitioning the L1 cache. There was no architectural support available for partitioning the LLC. But if there is such support, then yes, the partitioning will still, for like LLC, yes, the partitioning will still work. But it cannot work, it couldn't work at that time. Okay. And CAT itself was not designed for partitioning the LLC. Yes, it was designed for partitioning, but to achieve the quality of service, to meet the quality of service demand of different processes. Maybe each one of them have different demand, right? But they repurpose it to achieve the better security, not better quality of service. Okay. Okay, so, and even there is a more fundamental problem. There is a problem with cache allocation technology itself. Yes, you can use it just like I explained here. You put the spy and the victim in different class of service, and as a result, the ways in which their data is mapped is different, right? But there is a problem. The problem is that you can support only up to 4 class of services using CAD, right? So if you can support only up to 4 class of services, now consider the cloud server on which there are like much higher number of virtual machines running at the same time, right? And you don't know which one of them, let's say there are, 64 virtual machines running at the same time, and you don't know which one of them are spy. which one of them is a spy, or maybe there are multiple spies, right? So it means you need 64 different class of services. So then CAT will not work because it can support at most 4. So if it can support at most 4, then you need to divide these 64 virtual machines among 4 classes, like maybe 64 divided by 4, 16 per class, I don't know. Okay, depending upon their quality of service demand. But you cannot have 64 separate classes. So if as a result, there will be sharing, right? The spy will be ultimately end up sharing the class with some other processes. And then as a result, their data will be mapped into the same way. And then spy will be able to launch the attack. Questions? Okay, so here is like the same thing I'm trying to explain, which I said, just said. Let's say now, instead of 2 cores, you have 32 cores, right? And there are like, you can say, okay, virtual machine or processes doesn't matter because the argument we are making will be valid whether there are 32 processes running on the same machine or 32 virtual machines running on a host machine. So we don't know which one of them is spy. The virtual machine or the process running on core 31, is it a spy or not? We don't know. So if we don't know, we cannot trust it. If we cannot trust it, we need to put it in a separate class of service. And same is true for all of the virtual machines running, right? And we cannot support more than 4 classes of service using CAT. So yes, this side we can use the CAT. We want to repurpose the CAT, but this is the challenge, right? This is the limitation of the CAT, which they need to address in the paper. Okay, so anyone who want to share the main idea before I share with you? The main idea of the paper. Okay, even if you partially understand it, say it. Even if you have some understanding of it, you don't need to be 100% correct.
Is it the repurposing of CAT is they have one class of service for like secure pages where if your process has sensitive data, only it can use this page and no other core or VM could use it.
No other process or no other VM.
Yeah. And so then once it's kind of like locked in and safe, isolated is from what I understood. Kind of.
Okay, yeah. So actually the same thing what you said. So what they do is okay, we have this cache, we have CAT. CAT can support up to 4 classes, but we don't need 4 classes. We define 2 classes, right? So one for those applications which need secure processing. Like for example, let's say I am running RSA, okay, and I don't want my RSA to be broken by any potential spy there. So what I do is that I partition, I define 2 classes, secure class. So all the data for secure processing, it goes into the ways which belong to the secure class, ways of the LLC, right? And while my data is there, so I do not allow any other process to access those ways. Okay, so if other process want to run and it needs that LLC, it can use the unsecured class. Okay. So it's now instead of defining the classes from the perspective of quality of service, they are defining the classes from the perspective of security. So if you keep in mind the previous paper, so there they had spy and the victim, both for mapping the same library into their address space. Now, if I'm a victim, here what I can do is now I can ask that, okay, I need secure computation. So then they will map my pages into the secure class. And when I am mapped into the secure class, no one else is allowed to map its data into the ways belonging to the secure class. So you partition the LLC into 2 classes, and this is It is not like how you will like all the time partition the LLC like this, but this is like a very simple demonstration. It is not required that always W0 to W3 must belong to the secure partition, and W4 and W up to W7 must belong to the unsecure partition, but or unsecure class. But this is just one case, one instance where you can do. So any secure, so here in unsecure partition, any secure or unsecure application can run, right? But in the secure partition case, in the secure partition or class of service, what you do is that only secure application, for example, victim user, if you are like, if you are running your application and you know that you are doing some computation, are you accessing some data which is secret to you, which is sensitive to you, and you don't want it to be exposed, then you will tell the system that I need the secure class. And for that, what they do is that they do the secure pages of cache pin. Okay, I will come back to this, what cache pin is. So first thing is like, then they provide an interface, which I haven't mentioned here. They provide an interface which can be used by the application to request that my data or my code should be loaded into the secure partition. Okay. And secure pages, so once secure pages are put here, put in the secure class, they are also cache pinned. Anyone who knows what does it mean, cache pinned? What is the meaning of cache pinning a page?
Static,
Explain more.
like, making the page exclusive to the.
Cache pin is just like, I don't know, I haven't used Facebook for like 6-7 years, but I think back then there was an option like you can pin your post. So it stays at the top. Other posts, they keep going down. So it can, that post will not go down, right? Same here. When you pin the page in the cache, the data you have read, it will stay there. It cannot be evicted. It cannot be moved down. It will stay there. And as long as the page remains pinned in the cache. Okay. So even if you say CL flush, that page will not be flushed. Even if a conflict happens, you know, there are conflicts happen in the cache, right? Multiple addresses map into the same set. So if it is already occupied and there is no empty slot, you evict a victim. So if a page is pinned in the cache, even if there is a conflict, it will not be evicted. So there is no eviction. So, and if there is no eviction, keep in mind in the previous attack, if you cannot evict, you cannot launch that.
Is this something that like the user would do, or something that like your operating system or whatever programs you run, would they pin?
There must be a request. I don't know what are the particular details, how it is done, but there must be an operating system service which you can use to request pinning your page in the cache. Because I know, like, at least I have done this, and I know that what you can do is you can specify, okay, I am running this process and I have a chip with 32 cores and I want to run my chip on core number 5. So pin my process to core number 5. So you can ask the operating system to do that. So there must be a interface which allows an application to request the operating system to pin its pages in the cache and then unpin too, right? When you're done, you can unpin them. Yes.
So this is the locking mechanism that Catalyst implements to make CAT more secure, right?
Locking mechanism. You can say, and because there are also other options, there are other techniques which don't use the CAD, but even if the CAD is not supported in the architecture or the hardware, still you can do the locking. But that locking is like, the idea is similar. What you do is that you can say, okay, I am locking this particular cache line, and now any data cannot be evicted out of it once I have placed my data. Okay. So you can say that the idea is similar to locking. Okay. Any questions?
So if a cache pinned, is there another method to gain that information on that cache pin since you can't get it through flush or reload or prime and what's the other one? Prime and probe? Would there be another attack because it's?
If you can devise a mechanism which allows you to measure the timing of the victim without doing the eviction, then you can break this attack. And then you can break this defense mechanism. Because it depends, its cornerstone is like, since I am not permitting the eviction of my data, once I have pinned it, attacker cannot time my operation, right? So, but the attacker was depending or relying on the case, on the thing like I was able to do the eviction. But if attacker says, okay, I will not use the eviction, I will use some other mechanism, which I don't know. But there must be, if not, one can find. So if I can have some other mean other than the eviction to time your operation, then I will be able to break this back. And I'm sure this defense has already been broken.
Yes.
I had a question on like the aspect of the resource sharing of this, like, because in operating systems, when you're resource sharing, there's a guarantee of like a process when they're using a part of memory, there's like a guarantee they'll stop using it in certain polynomial time. And I don't know if there's a guarantee here, like, what if a spy or an attacker process says, oh, I'm a secure process and I need to use all the ways, and they just cache pin all of them.
See, this is how you can manipulate the things. If an attacker does that, what you are saying, everyone understood what he's saying? So if, let's say, I'm an attacker and I abuse the cat, and I say, okay, I want to use the secure class, and then I'm never going to unpin my pages. So now any other process which needs secure computation will not be able to run. And this is a kind of attack which is known as denial of service attack. But then there must be mechanism like you can build some you can include in systems and some kind of mechanism. Okay, this is the upper limit or time limit for which you can keep your pages pinned, and after that you must unpin them. And if you don't, then operating system will do it on its own. It will do the unpinning anyway and notify you to like avoid this kind of denial of service. We will read a paper in upcoming week, which is eternal war in memory. Who is going to present discussion lead on that? Eternal war in memory.
Next week?
I think yes. Yeah. So there you will see this kind of situation. It never stops. Attackers, they develop some kind of attack, defenders come, they propose the defense. Then the attackers break that particular defense, they propose new one. So it's never going to end. The only point, the time point where you are safe is like you have proposed a defense, and before an attacker becomes and break it, that is the time period when you can say, okay, my approach is still working. Okay. So virtualization, so I'm just trying to cover the background. Previous slide was also on the background here again. So in virtualization, how things work, like you have same platform at the bottom layer. The hardware is same. On the top of the hardware, you are running one operating system, which is named as host operating system. But then on top of that, there is an additional layer, software layer, which you name as virtual machine monitor. And then on top of that, you have multiple virtual machines running, right? Each virtual machine has its own guest operating system, and these guest operating systems in different virtual machines, they can be like same or they can be different, right? So, and then within each virtual machine, you can run multiple applications, right? So the job of this virtual machine monitor is to do the resource allocation and manage the resource allocation for virtual machines, and it also interacts with the host operating system. And its main purpose is to create this illusion for the virtual machine or any application running in a virtual machine that it is the only virtual machine or only operating system, guest operating system, I'm the only operating system running on this hardware. So it creates this illusion, okay? While the reality is that there are multiple operating systems running on the same underlying hardware. Yes.
Sorry, just really, is the VMM the same thing as the hypervisor, or is that?
Yeah, I'm not sure, but my feeling is that it is the same thing hypervisor, because hypervisor is also does the resource management among multiple virtual machines.
So it's pretty much the same thing, it's not like some other software
No,
replacing.
my understanding is that these are two names of the same. Okay. So now remember when we were talking, forget about virtualization, but let's say if you have a single operating system running on a same on the hardware, and it has multiple processes running. So remember what we do, we already said last time that the addresses generated by a process, they are virtual addresses, right? And they need to be translated into the physical address, for which we use the page table. So same still holds when you are running an application in a virtual machine. So, but that application is runs on top of the guest operating system, right? So let's say this application generates a virtual address. So what happens that, as like we do normally, we will look into the page table of that particular application. Every process has its own page table. So we will look into the page table of that process, and it will give us not physical address, the real physical address, because real physical address is one which actually you can use to access the memory, right? But it will gives us a understanding of how guest operating system understands the physical address, or its own notion of the physical address, which is different from the actual physical address. So which means, but if the application actually need to access the memory, it needs the actual physical address, right? So what we need to do is that we need to do another access another table, which actually what this table does is that you index it using the physical address and how physical address is interpreted by the guest operating system. You take that physical address and use it to index or look into this table, which gives you the host physical address. The host physical address means the address which is actually the address you can use to access the memory, right? And this shadow table, this is called shadow table, and this shadow table is also maintained per process. So every process has its own page table, and every process has its own shadow table. So why is it needed? Because your application is running on the guest operating system, but then guest operating system is not running on the actual hardware. It is interacting with the virtual machine, which is interacting with the host VMM, which is interacting with the host access, and then you have the physical address. So you need an additional layer of translation. Okay. Now, you know that where this page table is located, right? Where is this located? Page table.
Physical hardware,
Sorry.
physical hardware,
Yeah, but
outside the VM.
In memory, right?
in memory, right? So the traditional page table is located in the memory. Doesn't matter whether it is virtualized environment or not. The shadow table, which is needed only in this virtualized environment, it is also located in the memory. And remember, you need these two tables per process. And now is consider you have multiple processes running on each virtual machine, and you have multiple virtual machines running on the same place. So there are so many tables, right? Now, when you access the table, so you make first memory access, and then you make another memory access. And memory access is always expensive, right? So it slows down it slows down your application. So what they did is to avoid that, Okay, so the first page table lookup, it is handled by the guest operating system, but the second one is handled by the VMM or hypervisor. And but since this is extra, this this table lookup is extra as compared to the case where we don't have the virtualized environment. So this means that we are paying the extra overhead. So that's why what they did is like Intel introduced an extra architectural component, which they named as enhanced page table. So what it does is that here you are running the software this is your software instructions, a piece of code which you are running to access the memory, this table in the memory. But here what they did is that they implement the same thing in the hardware. And anytime you implement a logic in hardware, it is much faster as compared to doing the same thing in the software. So to make you understand it in more clearly, there is a classic example of multiplication. So if you want to multiply x, you want to write z is equal to x times y, right? So one way is that you do the multiplication operation, and the other way is that you do the repeated additions, right? So you add, let's say, y x times to itself, right? So you will get the result. Now the thing is implementing multiplier, you can do two things. Either you can have a hardware component which implements the multiplier, or you can have an adder and you can ask it to repeatedly add the same thing. Now, if you use the adder, your hardware will be simpler because addition is a simpler operation, but it will take longer. It will take more cycles because you will be doing repeated addition. On the other hand, if you implement the same logic in the hardware, like hardware multiplier, it will take less amount of time to complete. So the same, you can use the same analogy here, not exactly the same thing, but if you are doing something in the software, it will take more time as compared to if you implement the same logic in the hardware. So what they did is that they included an additional architectural component which takes care of the second step of looking into the shadow table. Okay. So remember we said that the job of the virtual machine monitor, VMM, is to provide the illusion to each guest operating system that you are the only one running on this machine. And by illusion mean that we don't want it to have any kind of hint that another operating system is also running on this machine. Because if you can guess that there is another virtual machine running, it's mean you are breaking that illusion. And if I'm breaking that illusion and I can get some data about existence of another virtual machine, I can exploit it to launch an attack, right? So there are some instructions that can break this illusion or this isolation. So if there is such a case, then what happens? Let's say that an application try to execute an instruction which has risk of breaking this isolation, the virtual machine monitor will take care of that instruction will actually trap into the virtual machine monitor. It is exactly the same case, for example, as in non-virtualized environment, when an application is running and it needs some operating system service, it makes operating system call, right? So then what happens? That operating system, when you make an operating system call, you are trapped into the operating system, which actually launch the handler, which is responsible to serve that operating system call, right? And then the application waits for that service to become available. So same thing here, when an instruction is executed, which the application is not supposed to execute, then virtual machine, it will trap into the VMM, and then VMM will emulate that instruction, okay? Execution of that instruction. One thing I would like you to ask is, go and check later, what is the difference between emulation and simulation, okay? Maybe for those, maybe I'm not a native English speaker, so I didn't know, but you can go and check what is the difference between emulation and simulation, okay? So, yes, the VMM will emulate and as a result, what happened that the logical effect of the state change will be visible only to the calling virtual machine. Let me try to give you an example. So the purpose of the emulation is this. In emulation, you actually, what you do is that you try to faithfully replicate the architectural components as themselves. So, like for example, you have this virtual machine running here, and you have this virtual machine, another virtual machine running on the same platform. But at the bottom, we have the same hardware. There is, let's say, only one LLC, right? So it's mean that both of them should not be able to view the LLC. So the job of the VMM is to deceive them by emulating an LLC for this virtual machine and an LLC for this virtual machine. So it actually models the LLC in the software. So that, and why it does so that if, let's say, it is if they have their own separate LLC in emulated form, then all the data which is coming to them, it will look like that all my data coming to my LLC is not affected by any other virtual machine, because every virtual machine has its own LLC. But if in the case, if it was not the case, if all of them had the same, so what will happen that if data goes here, it can also affect my timing and my performance, right? Like, how to make it more clear. So if same LLC is emulated between two virtual machines, virtual machine one will see more capacity misses if the same LLC is also accessed by virtual machine two. You know what are the capacity misses, right? I have occupied already the space, so there is no space left behind in the LLC. Relatively less amount of space is left behind in LLC for my data, and as a result, I will see more capacity misses, right? So in other words, from my perspective, you are polluting my LLC, right? So what they do is that they emulate and they just try to model two separate LLCs for each one of them, so that whatever data I am reading in, it should not create capacity misses for virtual machine one, okay? So that is good thing, but the issue is that these are only logical components. Like they are only your software modules, which you are using to imitate the behavior of the LLC, but they are not actual LLC. They are not hardware components. The data still is coming from the underlying hardware, right? So this is still shared. The actual LLC is still shared, right? So this creates the contention. And since this creates the contention, it breaks the temporal isolation. Temporal isolation means that the latency I see for my data to be accessed in my, become available in my emulated LLC, it actually depends how many shares are there for my actual physical LLC, right? Because the data still is coming from there into my emulated LLC. So that is still a shared bottleneck, okay? Any questions? So basically the takeaway of this slide is like, there are still shared side channels available in the virtualized environment, which can be exploited, and LLC is an example of that. Any questions? Okay, who want to explain prime plus probe attack? How it is different from plus reload?
This was first implemented But no, basically the flush and reload was based on this one, right? On program
No, flash bus reload is not based on this one.
or improved version, something like that? Cause
Sorry?
I think it was mentioned on the paper, was it?
That flash bus reload is based on prime plus flow.
Or they at least mentioned it.
They are similar, but they have also differences. Not same. Wrong answers are also accepted, so fine if you want to give a wrong answer, that's okay also. Okay, so in flush plus reload, the first thing is like it requires the data to be, it requires the page sharing between the victim and the spy, right? Here, we don't need the page sharing, okay? And the second thing is that in flush plus reload, what you were doing is like, as I said, there are similarity, both have 3 steps. Flush plus reload, what you do in first step as a spy, you flush your cache lines, right? And second step, you wait for the victim to do for some amount of time. And third step, you go and read the same flushed cache lines. You try to read your data. Okay, and depending upon the timing, you detect whether it was loaded by it was accessed by the victim or not. Here, what you do is, again, you have 3 steps. But in the first step, instead of flushing, what you do is that you fill the cache line with your data. You don't flush it, okay? And how you know which cache line to flush? So there is an assumption. The assumption is like, victim's address. You know the victim address. Sorry, I don't know. I'll type it correctly. So you know the address of the victim's data, which is of interest to you, but you cannot access that address. You don't have the permission to access that address, but you only know that address, right? Now, if you know that how the addresses are mapped into the cache set, it depends actually on the addresses, right? Which I will try to explain. So if I know the address which is of interest, the address of the victim's data, then I can figure out, okay, based on this address, into which particular set it will be mapped, in which particular set of the cache it will be mapped, okay? And then I can figure out, okay, if this is the set, which of my data will also be mapped into the same set, right? So I figure out that set first, based on the address. If I have address, I can get the set number into which the address of the victim will be mapped. So let's say it is the set X. The second question is, what I will do is that I will figure out all those my addresses of my data, which will also map into the same set. And then what I will do is, remember, one set has multiple ways, right? So let's say this is set X. So what I will do is that now I will start filling this set with my own data, right? So let's say my data is Y. Okay. Then I wait. This was first step, where I'm priming this is called prime step, where I'm priming the cache set. Then I wait for the victim to execute for a given amount of time. How long, I don't know. But the idea is that you wait. How to decide it? It is a different question. What is the wait period? But you wait for some amount of time in which you expect that the victim will do some access. Okay. So if victim does some access and it puts its data, let's say its data was Z. So it is like, so it will evict this Y and put the Z here, right? Now, next time what I do, I come and I read my data. Let's say this was Y1, Y2, Y3, Y4, Y5. I try to write Y2, but Y2 is not there. I result in a miss. I see a miss in the cache. So it will tell me, oh, the victim has accessed this particular cache line. Okay. And if I see that, oh, my data is still there, it's mean the victim didn't access this particular cache line. Okay, so first, there is no sharing. This is RAM, this is attacker's memory, attacker's data, and this is victim's memory or victim's data. And they are not shared, they are not doing the page sharing here, okay? But I know the address, the memory address of the victim's data. As an attacker, I know the address, but I cannot access that address. I don't have permission. So based on address, I know where it will be mapped in the cache. So then as attacker, first I do the priming step where I put all my data here. So ignore this yellow block here. I put all my data in the cache set. Let's say this is set 0, whatever. Okay, whatever set X, let's say. So I fill it with my data. And then I wait for the victim to run. When victim runs and it accesses its own data, it will put it in one of the cache lines in that set, right? And then I can come back and try to read my own data from the same cache set. And if I see that it is taking me longer, then it's mean that the victim has placed his data there. By the way, why I'm saying that attacker will place his data in one of the cache lines in the set. So the address always maps only to a set. And inside the set, you have particular cache lines. Address don't tell you that in which particular cache line that data will be placed. It depends upon the availability. And it also depends upon, like, let's say if all the cache lines are already filled, you need to select a victim. What is your policy for selecting a victim? For example, least recently used. This is like most popular used policy. So what happens is that depending upon, let's say if all of this is fulfilled already by the attacker, so which one was least recently used, that particular cache line will be affected. It can be this one, it can be this one, it can be this one, this one, this one, depending upon the history, which one was least recently used. Okay. Let me finish this slide and then we take the not break, then we can stop. So the difference from flush plus reload is that prime plus probe, it does not need page sharing between victim and spy. It only need to, the attacker only need to know the address, okay? Okay, why flush plus reload needs page sharing? Well, you know it, right? After reading the previous pages, paper. But why the page sharing is needed?
It's getting that information from the same page that the functions are running. So they're sharing the data and the victim is able to defer those time differences because it's able to
Yeah.
accept the same page.
So if the pages are not shared, remember, keep in mind the previous lecture. If the pages are not shared as an attacker, I don't know what is the address of those variable, multiply variable in the example, or modulo variable, or, but if I don't know their address, then I cannot access them, right? I need to access those variables. And in order to access them, I need to share them with the victim. If I don't share with the victim, then victim will have its own variables, for which I don't have access. Okay. Prime plus probe needs to know target address of the victim, but don't need access to that. You don't necessarily need to have access permission for that address, but you need to know the address. And the mapping function that maps a physical address to a particular set of MLC. We will talk about more on this in the upcoming lecture, but how the question basically, and the point number 2 is like how the address is mapped into a set. Like based on address, how can I figure out in which particular set of the cache this data will be placed? Okay, any questions? No? Seems like relatively the class is less involved I don't know why. Maybe you guys haven't read the paper yet. Or maybe, I don't know. But I would like to see